acceleration. An electron is a charged particle also. So according to the Maxwell, electron will radiate some energy or emit some energy. If the electron will emit some energy, due to that, what will happen? Electron will be attracted towards the nucleus. Earlier, electron is revolving around the nucleus in a particular orbit, but now electron is radiating energy, and due to uh, electron is emitting energy, so means that electron's energy will decrease, and due to decrease in the energy of electron, okay, due to decrease in the energy of electron, electron will move towards the nucleus, and the uh, path of the electron will become like this, and after some time it will strike with the nucleus and atom will destroy it. Means this universe will destroy it, because everything is made up of atom. So basically this is not correct. This theory of Rutherford was not correct. Okay. So electron has acceleration. Electron is a charged particle. Electron continuously emits radiation, and due to that, the electron will fall into the nucleus and atom will destroy it. Secondly, the Rutherford model cannot explain the discrete spectrum of atom. Cannot explain the discrete spectrum of atom. So what is the discrete spectrum of atom? I will explain you later. Okay, because we will study spectrum. So in what happens in discrete spectrum? We know that a white light is having 7 colors. So basically, on passing the white light from a prism, we get a band of 7 colors. Basically, that is the continuous spectrum. Means all wavelengths are there. But in case of the discrete spectrum, there are only particular wavelengths available. So that is the discrete spectrum. Okay. So according to the Rutherford, electron can revolve in any circular orbit. Electron can revolve in any circular orbit. Okay. So if electron can revolve in any circular orbit, means electron will give the continuous spectrum. You will know how. So after the failure of this model, Rutherford model, there was a scientist, Neil Bohr. So he gave his atomic model. So now we will study the Bohr's model of atom. So in Bohr's model of atom, basically this is a Bohr's model of atom. So Bohr give his atomic model with some modification in Rutherford's model of atom. So in 1930, Bohr gave his atomic model with some modification in Rutherford model. So there are few points that we will cover in Bohr's atomic model. First point, electron can revolve only in certain stable orbits. But according to the Rutherford, electron can revolve in any of the orbit. But according to the Bohr, electron can revolve only in certain stable orbit. These orbits have fixed energy, and these are called energy levels or stationary state. And these were named KLMN. So basically, you can see here, this is the nucleus. This is first energy level, second energy level, according to the Bohr, third energy level. So electron can revolve only in these energy levels, and these energy levels have fixed energy of, and these energy levels were named as KLM. Okay. So energy of K energy level is 13.6 electron volt, and L minus 3.4 electron volt, M minus 1.5 electron volt. We will discuss this in detail. After that, electron have same energy as that of orbit in which it is revolving. For example, if electron is revolving in K orbit, K energy level, so the electron energy will be equal to this, and this is the energy of orbit. Third, while revolving in a particular energy level or orbit, electron do not emit any radiation. So this is the most important point here. According to the means according to the Neil Bohr, according to the Bohr's atomic model, while revolving in a particular energy level, suppose the electron is revolving in k energy level. So until and unless the electron is revolving in k energy level, electron will not emit any radiation. So basically, he applied means Bohr applied here the quantum mechanics. Okay, so basically we cannot use here the classical mechanics. According to the classical electromagnetism, if the electron will move in a circular path, it will radiate energy according to the classical electromagnetism. But according, we have to change that. Okay, we cannot apply classical mechanics here to explain the atom, to explain the phenomena inside the atom. We cannot apply 100% the classical mechanics. So here there will be a use of the quantum mechanics. So according to the quantum mechanics, he said that while revolving in a particular energy level, electron do not emit any radiation. Okay, now when the electron will not emit any radiation, so it will not fall into the nucleus. Problem is solved. Another point, if electron absorbs or emits energy, it must move to a different energy level. For example, if electron is here, okay, if an electron is supposed in this energy level here, electron is revolving in k energy level and you are giving energy to the atom. So this electron will move to higher energy level. This can happen. Now defining the stable orbit. This is very important point. Electron can revolve only in those circular orbits for which the orbital angular momentum of electron is an integral multiple of h upon 2 pi, and h is the Planck's constant. Means, suppose electron is revolving in this orbit. So if the electron is revolving in this orbit, the angular momentum of electron while revolving in this orbit is equal to integral multiple of h upon 2 pi. Okay. For k shell, for k energy level, n equal to 1. For L energy level, n equal to 2. For M energy level, n equal to 3. So if electron is revolving in first energy level, so angular momentum L is integral multiple of h upon 2 pi. And what is n? N is an integer. So while revolving in, now I am saying, for example, assume electron is revolving in first orbit, first energy level. So here you have to put the value 1, h upon 2 pi. So while the electron is revolving in first orbit, the angular momentum of electron, L is the angular momentum. Angular momentum of the revolving electron will be h upon 2 pi. Similarly, if the electron is revolving in second energy level or L energy level, so for L, n equal to 2, so you will put n equal to 2 here. Okay. Okay. So you can see angular momentum of electron either h upon 2 pi in first orbit, in second orbit, third orbit, fourth orbit. L cannot be like this 1.5 h upon 2, because here should be an integer. So basically we can define that angular momentum L is the angular momentum is equal to angular momentum of a revolving electron is equal to nh upon 2 pi. N is the integer, integral multiple of h upon 2 pi. Now angular momentum, if something is revolving in a circular path, electron is revolving in a circular path, so angular momentum is cross product of r into mv. So from here we can calculate the angular momentum. L is equal to r mv sine of 90 degree. Why? Because this is radius r and this is velocity. So this angle you can say will be 90 degree. So you will use sine 90 degree. So it will become MVR. Okay. So you can say that angular momentum of electron is MVR, and this is equal to integral multiple of h upon 2 pi. Sixth point, this is also an important point. While revolving in a higher energy level, while revolving in a higher energy level, an electron may emit radiation of a specific wavelength, and false means you can see here. Suppose electron is here. Suppose electron is here. Oh, sorry. Suppose electron is revolving in this energy level. Okay, in this electron is revolving here. Okay. Now, when electron will move from higher energy level to the lower energy level, basically this is lower energy level, and these are higher energy level. So you can see energy of this level is minus 13.6, minus 3.4, minus 1.5. In negative, the energy is decreasing, means energy is increasing. So energy of K level is less than L level, energy of L level is less than M level. Okay, so electron is in L level revolving. So suppose the electron is moving from higher energy level to the lower energy level. So what will happen when the electron will move from higher level to the lower level? So electron will emit energy. Electron will emit energy in the form of the photon. And when the electron, suppose, is moving in a lower energy level, and from that lower energy level, okay, if electron is going from lower energy level to the higher energy level, it means electron will absorb some energy. After absorbing some energy, the electron will go to the higher energy level. Okay. So this is written here. While revolving in a higher energy level, an electron may emit radiation of a specific wavelength and falls to a lower energy level. Okay, the energy of such photon is always equal to the difference in two energy level. And one more thing here, suppose the electron is revolving here and moving to here. So during this process, when the electron is going from here to here, during this process, the energy released will be the difference of energy levels. Okay, energy of this level, energy of minus this level. Same thing written here. While revolving in a lower energy level, an electron may absorb radiation of a specific wavelength and jumps to higher energy level, and the energy of such photon is always equal to the difference in two energy levels. So this is the Bohr's atomic model. This is the Bohr's atomic model. After this, with the help of this atomic model, we will calculate the radius of the orbit, velocity in a particular orbit, energy in a particular orbit. So first we will calculate the radius and the velocity in a particular orbit. So now you can see that electron is revolving. This is the nucleus, and electron is revolving in a specific orbit. So electron is revolving in a circular path. Okay. So on electron, there will be the electrostatic force, because electron is negatively charged and nucleus is positively charged. Okay. So this will be the electrostatic force. Okay. Now one equation is this. Angular momentum of the electron MVR is equal to NH upon 2 pi, we know. And one more thing. If okay, what will be the electrostatic force between the electron and the nucleus? So electron is here, nucleus is here. So on electron, the charge is E, And on nucleus, the charge is Ze. Z is the atomic number and E is the charge on electron. So electrostatic force you can calculate, and electron are and nucleus are separated by a distance of r. Okay, so you can write electrostatic force K is 1 upon 4 pi epsilon naught, and Q1 is E, Q2 is Ze divided by r square. Okay, this is the electrostatic force of attraction. Now, this electrostatic force of attraction is providing the necessary centripetal force to revolve in this orbit. Because electron is revolving in a circular orbit, so there is a requirement of centripetal force, and that is provided by this electrostatic force. So basically, this centripetal force is provided by the electrostatic force. And what is the centripetal force? So the formula to calculate the centripetal force: mass of the electron, square of velocity, divided by radius of the orbit. And electrostatic force is this. Okay. So from here, this is equation number second. This is equation number second. So this is equation number first. This is equation number second. When we solve equation number first and equation number second, we will get the radius of the orbit. So what we will do, we will, because here is mv square by r and here is mvr. So we will square equation number one. We will square the equation number one and divide this equation number one with second. So we will get uh, square of first. We will get m square v square r square. So it will be m square v square r square divided by this value mv square by r. And on right hand side, square of this n square h square divided by 2 pi square. So it will be n square h square divided by 2 to the 4 and pi square, and divided by this value. Divided by this value. So when you will cancel out all these things, means you can see here this v square will be cancelled out with v square. Okay, this 1m is cancelled by 1m. Okay, and when you will multiply this thing here and this thing here, you will get mr square. Mr square is equal to n square h square epsilon naught r divided by pi z e square. From here we can calculate r. R will become mr square pi z e square by n square by h square. Okay, so r will become we have to solve it again. So what is this? This is m square v square r square divided by mv square by r. And what is this? This is n square h square divided by 4 pi square, and this is E into ZE divided by 4 pi epsilon naught R square. Now we will solve it. It will be m square v square r square divided by mv square by r, and on this side we can write this value first, n square h square divided by 4 pi square multiplied by, this will be in the numerator, this will be in the denominator, 4 pi epsilon naught r square divided by z e square, because this is z, this is e square. Now cancel the things from this side. This pi is gone with pi. Okay, this 4 is gone with 4. And what is cancelling out here? N square, h square, z e square, epsilon r, nothing is cancelling out. But from here you can cancel this r square and any other thing. Now from here this is cancelling out, and from here this is cancelling out. Okay, now you will get r. You will get r is, this will be, this is 1 by 1 by r, 1 by 1 by r, it will become r, that is equal to n square h square epsilon naught divided by pi z square. Okay, and this is m also. So here you will get, this is this m will be multiplied here, so it will become r is equal to n square h square into epsilon naught into this m is here multiplied, m multiplied here, m into pi into z square. So this will be the final answer. This will be the radius of nth orbit. Radius of nth orbit. So this is the formula, okay, for nth orbit. Put the value of n, you will get different radius of different orbits. Okay. After that, because here is the electron, so for electron, if we will put the value of h, because h is the Planck constant, epsilon naught is also a constant, absolute permittivity, mass of electron, m is the mass of electron, pi, the value of pi we know, charge we know. Okay, now here put the value of h, e, epsilon naught, okay, m. Okay, when you will put all the values here in this equation, so you will get this formula. Okay, and you have to remember this formula for the radius of nth orbit. For radius of nth orbit, you should learn either this formula you should learn, 0.53 n square by z angstrom. 0.53 n square by z angstrom. What is r? R is the radius of nth orbit. Radius of nth orbit. Okay, when you will put n is equal to 1, you will get radius of first orbit. When you will put n is equal to 2, you will get radius of second orbit. Accordingly, atomic number z means for which element you are calculating the radius. For example, for hydrogen, suppose for hydrogen you want to calculate the radius. For hydrogen, what is the atomic number? 1. And you are calculating for hydrogen the radius of first orbit, means n equal to 1. So how you will calculate? This is the formula. So in this formula, you will put 0.53 n square. N is 1. 1 square divided by z is also 1. So you will get the answer in angstrom. So basically it is coming out to be 0.53 angstrom. Now for n is equal to 2, means radius of second orbit. So it will be 0.53 multiplied by n square by z. N is now 2. So 2 square, and for hydrogen atom we are calculating, so n will be 1. So it will be something of angstrom. Now similarly you can calculate for n3. Now if they are saying calculate radius for second cell of helium, second cell of helium means n equal to 2, and for helium the atomic number is 2, z is the atomic number, so put the value in this, you will get the value. Okay, now second excited state of lithium, second excited state. So second excited state means this is first, this is second, this is third. So this is the ground state, this is the first excited state, this is the second excited state. So for second excited state you will take n is equal to 3, and for lithium atomic number z is equal to 3, and apply this formula, you will get the answer. Now velocity to now radius to calculate, radius is bit uh, uh, lengthy, but to calculate the velocity is very easy. For calculating velocity, we know that mvr is equal to nh upon 2 pi. Put the value of r here. When you will put the value of r here, it will be nh upon 2 pi. Okay, and when you will cancel all these things, cancel out all these things, you will get this, and finally the velocity you will get this. I am leaving calculation on you. So velocity of electron in nth energy level. Velocity of electron in nth energy level is this. Okay. Okay. Hello, Nafisa. Hello. Nafisa, are you getting my voice?
Yes, sir.
How are you?
I'm fine, sir.
Okay. So we are discussing the Bohr's atomic model, and we are calculating the radius and the velocity of electron revolving in different energy levels or different orbits. Okay, so this is the velocity, and when you will put all the values, means E is the charge on electron, H is Planck constant, epsilon naught, so you will get this velocity formula. You will get this formula for velocity. Okay, this formula you will use. Okay, this formula to calculate the velocity. Okay, because when you will put all the values here, you will finally get this formula. For example, for hydrogen atom, if you want to calculate for n is equal to 1, for ground state you want to find the velocity, so what you will do, 2.18 into 10 to the power 6 divided by multiplied by z by n. So put the value of z1, put the value of n1, so 1 by 1 it will 2.18 into 10 to the power 6. Suppose they are asking find the velocity of electron in first excited state of helium. First excited state means n is equal to 2. N is equal to 1 is the ground state. Oh, n is equal to 1 is the ground state. N is equal to 2 is the first excited state. So n is equal to 2, and helium, atomic number of helium 2. Now formula for calculating the velocity is this, 2.18 into 10 to the power 6 multiplied by z by n. So it will be 2.18 into 10 to the power 6. What is z? Z is 2, n is also 2. So it will be 2.18 into 10 to the power 6 meter per second. After the radius and the velocity in the orbit, we will calculate the energy in the orbit. So basically, there are two types of energies that the electron have in an orbit. That is, first is the kinetic energy, another is the potential energy. And sum of the kinetic and the potential energy is total energy. So energy in the orbit. So this is the whole story I told you what is happening here. Okay. Once again, Nafisa, see, this is the nucleus and this is electron, and electron is revolving in a circular orbit around the nucleus. Okay, charge on electron we will take minus e, and charge on nucleus we will take Ze. Z is the atomic number. Z is the atomic number. And I told you that at each and every point that there is a change in the direction of the velocity, by the way. So kinetic, and suppose electron is revolving in this orbit. Electron is revolving in a particular orbit. Okay. So kinetic energy of electron is half mv square. So half m into v square. Now we know that the velocity in nth orbit is this. So we will put this value and we will get the answer. So it will be half m v square, means square of this. Okay, square of this. So it will be half, it will be m multiplied by, it will be z square e to the power 4 divided by, this is 2 to the 4 h square epsilon naught square into n square. Finally, it will become mz square e to the power 4 divided by 8 h square epsilon naught square into n square. So this is the kinetic energy in nth orbit. Kinetic energy in nth orbit of electron. Now potential energy of electron. Potential energy for a system of two charges, because this is the electron and this is the nucleus. So both are separated by a distance r and having charges also. So this is q1, this is q2. So potential energy is given by potential energy of a system of two charges in electrostatic. You have studied. It is given by k q1 q2 divided by r. So k is 1 upon 4 pi epsilon naught q1 q2 by r. So 1 upon 4 pi epsilon naught q1 charge on electron, q2 charge on nucleus, divided by radius. This is radius. Radius formula, just we have calculated the expression for the radius r. Radius r. This is the expression for the radius r. We will put here, and finally when we will calculate, we will get this value. I am not calculating this because we have very less time, very less time. If I will calculate this, then more time will be taken, and I think the syllabus will not be completed. Okay, so total energy. Now total energy is the sum of kinetic plus potential energy. So kinetic energy is this and potential energy is this. So add this plus this. It will be this plus this. When you will adding na, so this is plus but this is minus, so it will be subtracted basically. So it will become this. You can take this LCM na, 8h square epsilon naught n square. You will take this LCM. So this is mz is e power 4 minus 2 mz e to the power 4. 1 minus 2 means 1. So it will become this formula. This is the total energy. Now remember this thing. This thing is very important. You should learn this. Potential energy is equal to minus 2 times of kinetic energy is equal to 2 times of total energy. Now when in this total energy, we will put all the values, means m is the mass of electron, charge on electron, Planck's constant, relative permittivity, and all these we will put. So if we will get this value, and you have to learn this formula. Total energy, I am marking the stars, whatever you have to learn. So for calculating the total energy, this formula will be used, minus 13.6 Z square by N square electron volt. This is the energy in nth orbit, total energy in nth orbit. Now if they are asking kinetic energy, then from this expression you can calculate this. We will do one question on it also. And this is another point. You can see this total energy is negative. So what is the meaning of total energy is negative? If total energy is negative, means this electron is bounded to the nucleus. Means you have to supply some extra energy to free this electron. You should know in chemistry there is one thing, ionization energy. The amount of energy given to an electron to make it free. That is the ionization energy. Means you are giving some extra energy to electron to make it free. So basically, electron is bounded. So initially, the energy of the electron is negative. So a negative energy indicates that the electron is bounded to nucleus. And this is the formula of total energy in electron volt. If they are asking in joule, then this will be the formula. Otherwise, you can calculate. Means otherwise you can calculate. In 1 electron volt, there are 1.6 into 10 to the power minus 19 joules. So this also you should learn. For example, I am telling you how you will calculate. For hydrogen atom, we know Z is equal to 1. Energy of first orbit. Energy of first orbit. Energy of first orbit for hydrogen atom. 13.6. Z is 1 for hydrogen atom. So you will put Z is equal to 1. First orbit means N is equal to 1. N is equal to 1. So put N is equal to 1 here. So 13.6, 1 by 1, you will get 13.6 electron volt. This is very easy thing. Okay, this formula is there. You know the value of Z, you know the value of N. This is the energy in ground state. Now for second orbit or for first excited state, N is equal to 2. So energy in second orbit will be 13.6 Z square by N square. Apply this formula. When you will put the value of Z1, because Z is equal to 1 and N will be 2, so it will become this. So this is for first excited state. Simply for other second excited state, this will be the energy fourth excited 6, 7, 8, 9, 10, 11, 12. You can calculate by applying this formula. If you want to find the energy in electron volt. After this, there is energy level diagram. Now you can see in case of the hydrogen atom, for the hydrogen atom, for first orbit, the energy is minus 13.6. For N is equal to 2, the energy is minus 13.4. For N is equal to 3, this is N is equal to 3. The energy is minus 1.5 electron volt. So energy level diagram will look like this. This I have taken from NCERT. Now you can see here. For N is equal to 1, the energy is, this is the graph between total energy in electron volt, and basically this is a line. On this line we are showing the energy. So for N is equal to 1, the energy is 13.6 electron volt. Now for N is equal to 2, the energy is minus 3.40. For N is equal to 3, energy is minus 1.9. 15 electron volt. For n is equal to 4, energy is minus 0.85 electron volt. Now, for n is equal to infinite, energy will become 0. And when electron, okay, wait for Azan. Okay, so when you can see here, this is unbound ionized atom, means electron now is become free. When the electron is it becomes free, so energy of the electron will become 0, and that is for n is equal to infinite. Now, this was the Bohr's atomic model, and there are some limitations of Bohr's atomic model. In 2 minutes, we will finish that. Now, after so much of hard work, so much of time given by the Bohr, basically this is only true for hydrogen atom. So sad. It stands true for hydrogen atom and hydrogen-like atom. We cannot apply the Bohr's model on each and every element. Oh, not, no. This is only applicable to hydrogen atom and hydrogen-like atom. You can see single electron species, because hydrogen have single electron now. So if you have helium plus, lithium plus, barium plus plus plus, so you can apply the hydrogen Bohr's model of atom. Basically, this is true for hydrogen and hydrogen-like atom, like this. These are hydrogen-like atom. Second point, it cannot explain the spectrum of multi-electron species. For example, if I am giving another element that is having, suppose I am giving sodium. Sodium have multi-electron, okay, not one electron. So it cannot explain the spectrum of those. Spectrum, we will have a separate topic. Okay. Spectrum is basically the range of wavelength appeared on the screen. Okay. Third point, it does not take into account the wave nature of electron, violating the de Broglie hypothesis. So basically, Bohr's does not did not take into account the wave nature of electron. According to the de Broglie hypothesis, what was the de Broglie hypothesis? De Broglie said that electron shows the wave nature also, but Bohr does not did not take into account the wave nature of electron, and it violates the Heisenberg uncertainty principle. Now, what is Heisenberg uncertainty principle? At a particular time or simultaneously, I'm telling you what is Heisenberg uncertainty principle. Simultaneously, we cannot calculate the position and the momentum of electron. But according to the Bohr's model, we can calculate the position of the electron, that is radius, and radius is representing the position, momentum of electron, mass of the electron, velocity. We have an expression for velocity. So from this we can calculate the. So this we can calculate simultaneously, and that is not in accordance with the Heisenberg uncertainty principle. For example, for n is equal to 1 for hydrogen atom, so radius R1 will be 0.529. Okay, so remove this, no need. Fifth point, it cannot explain the splitting of spectral line in electric field and magnetic field. So basically, the spectral lines that there are some spectral lines, okay, of different colors. So in the present of electric field, those spectral lines will get splitted, and this effect is known as the Stark effect. Stark effect. And when the electric splitting of spectral line in electric field is Stark effect, splitting of spectral line in magnetic field is Zeeman effect. So these two effects could not be explained by the Bohr's model of atom. So these are the limitations of Bohr's model of atom. Now spectrum, what is the spectrum we will see. So first is the continuous spectrum. Basically, in detail, we will study emission spectrum, but before that, you should know what is continuous spectrum. This is a prism, white light. It will split into 7 colors. Basically, red, orange, yellow, green, red. Oh. Red, orange, yellow, green, blue, indigo, violet. And this is the screen. So white light will pass from the prism and you will get a band of 7 colors. And these colors having the wavelength range from 400 angstrom to 800 angstrom. And on the screen, you will get this type of thing. This is known as the continuous spectrum. So here all the possible wavelengths are presented on the screen. Basically, this is on screen. So this is the continuous spectrum. You can see all wavelengths are available here of visible region, 400 angstrom to 800 angstrom. Now, what is the emission spectrum? Basically, spectrum is of 3 types. One is continuous spectrum. This is the continuous spectrum. After that, there is one emission spectrum, and after that, we will discuss the absorption spectrum. So first, we will discuss the emission spectrum. Very easy. What is emission spectrum? So basically, to explain this, suppose this is some container. Okay, suppose this is some container, and in this container there is a gas. There is a gas filled, and what you have done, suppose hydrogen gas is filled here, and through the current, by passing the current through this, okay, due to the heating effect of current, this gas is heated. Means with the help of current, you heated this gas. So when the gas will be heated, okay, when, just a minute. When you will give the, when the gas will be heated means you are providing the energy to the gas. So radiation will come out from the gas. Okay, these radiation will come out from this gas, and when this radiation you will pass through the prism, you will get a spectrum on the screen, and you will find on the screen you are getting only specific wavelength. Some specific wavelength was present on the screen. Not all the wavelengths from 400 angstrom to 800 angstrom you are getting there. Here there are all visible wavelengths, but here means here you are getting all possible colors. But here you are getting not all possible colors, not all possible wavelength. You are getting some specific wavelength on the screen, and this will look like this. These only these colors, this type of spectrum you are getting, otherwise it is dark. Here there is no color, means no wavelength. This type of picture will be there, only some specific wavelength are visible on the screen. Okay, and here will be dark, here will be dark, here will be dark. So this is the emission spectrum. This will be the emission spectrum. So why this emission why this happened? Why this happened, that I will explain you. And remember, if instead of some instead of this hydrogen gas, if you have any other gas, you will have different emission spectrum. Okay. Now why this happened? Explanation. We know that we are taking the example of the hydrogen atom. We know that first energy level, second energy level, third energy level. Each energy level have a fixed energy. So this is K energy level, means first energy level will have 13 minus 13.6 electron volt, 3.4, 1.5. Actually, what happens on heating, electron jumps to higher energy level. So suppose here is the electron initially, and you are giving, sorry, suppose here is the electron, and you have given some energy to the electron, means you can see absorbing photon. This photon means electron is absorbing energy. So after absorbing energy, the electron will move to the higher orbit. Suppose the electron goes here or moved to here. But what happened here, in the higher orbits or to the higher states, or you can say in the excited state, the electron is not stable. Electrons want that it should be always on the ground state. Okay, so from here again the electron will come to, this electron will be here. So you have given the energy, due to this energy electron moved here. Now electron is unstable here, so from here the electron will move to the lower energy state, and when the electron is moving to the low energy state, the electron will emit photon of energy. And what I told you, energy of the photon emitted by the electron will be the difference in the energy level. So energy of N2 minus energy of N1. If the electron is moving from, suppose this is N2 and this is N1. So electron is moving from N2 to N1. So energy of N2 minus energy of N1. So you can see here, electron is very unstable in higher energy level, means excited state. So electron jumps back to the lower energy level and emit energy in the form of radiation or photons. Okay. Energy of such photon, I told you this, energy of such photon is equal to the difference in the energy of the two orbit involved in transition. Suppose the electron is moving, doing transition from N2 level to N1 level, so energy of the photon will be. Now see the story from here. Energy of the photon emitted by the electron is given by hc by lambda, and this value is the fixed value. This value is the fixed value. You can see if the electron is moving from this energy level to this energy level having energy of 1.5 minus 1.5, and this energy level having the energy of minus 13.5. Difference of this will be fixed. means the wavelength will be fixed. So that is why we get the discrete or the line spectrum. So lambda will have certain specific value only. Okay, because this value is the fixed value. So lambda will also have the fixed value. So that is why there are some fixed wavelength that we are getting in the emission spectrum. Understanding, Nawal and Nafisa?
Yes, sir.
Yes, sir.
Now, wavelength of the emitted photon. Okay. Okay, I am just taking a break of 1 minute. Okay. Okay. Now, you can see here electron is moving from higher energy level to the lower energy level, releasing a photon. So this photon will have a specific wavelength, and we will calculate now this wavelength. So basically, when the electron is moving higher to lower energy level, so it will be given by En2 minus En1. Okay. So energy of photon is given by hc by lambda, and energy in N2 orbit. Energy in N2 orbit is given by means energy of the energy in any orbit is of electron is given by minus 13.6 multiplied by z square by n square. If the electron is in N2 orbit, so you will write minus 13.6 into z square divided by n square, N2 square. Here the electron is doing transition from N2 to N1. And here is minus. Again En1 you can write minus 13.6 multiplied by z square divided by n1 square. Okay. Now you can take 13.6 common. It will be hc by lambda. Okay. So here it will be minus 13.6 z square by n square, and here is minus minus plus 13.6. This is n2 square. 13.6 z square by n1 square. Now hc by lambda is equal to, now take 13.6 and z square common. 13.6 z square common. So what you will have, 1 upon n1 square minus 1 upon n2 square. Now we want to find the wavelength, so we can find it. So wavelength will become 1 by lambda is equal to 13.6 z square divided by hc, and it is 1 upon n1 square minus 1 upon n2 square. Okay, now when you will put this value of h is 6.626 into 10 to the power minus 34 joule second, and c is the speed of light, 3 into 10 to the power 8 meter per second. So when you will put this value here, so you will get 1 upon lambda is equal to okay, if you will calculate this value, 13.6 divided by HC, so you will get 1.09 into 10 to the power minus 7 meter inverse, and this is R, and this R is known as the Rydberg constant. Rydberg's constant. So instead of this 13.6 divided by SC, you can put R. So basically you will have the formula 1 upon lambda is equal to RZ square multiplied by 1 upon N1 square minus 1 upon N2 square. Okay. So I will not recommend you to learn the value of R. Instead, you should learn the value of 1 by R. Basically, 1 by R is approximately equal to 911 angstrom. I will solve question, then you will know. Okay. So basically, this formula you should learn. So this form. I am making a star, whatever you have to learn. Okay, this is the formula. What is this? Lambda. Lambda is the wavelength. Lambda is the wavelength of photon. This is the wavelength of emitted photon during transition between energy levels. Okay, so I have one question. This is first question. Okay, so see here. For find the wavelength of photon. Find the wavelength of photon when electron falls from, and we are calculating this for hydrogen atom. Falls from n is equal to 2 to n is equal to 1. N is equal to 2 to n is equal to 1. So this is very easy. Answer first. So electron is moving, electron is falling from higher energy state to the lower energy state, because this will be the nucleus. This will be n is equal to 1. This will be n is equal to 2. This will be n is equal to 3. This will be n is equal to 1, n is equal to 2, n is equal to 3. So electron is moving from 2 to 1. Now electron is moving from here to here. And we have to find the wavelength when the electron is moving from here to here. So 2 to 1 means n2 to n1. So n2 value is 2, n1 value is 1. So we will put find lambda. 1 upon lambda is equal to r into z square. 1 upon n1 is square minus 1 upon n2 square. So 1 by lambda r z. For hydrogen atom, z is equal to 1. Z is the atomic number. For hydrogen atom, you will take z1. So it will be 1 square. 1 upon 1 square minus 1 upon 2 square. Okay. So it will be 1 by lambda is equal to r, and here you will get this is 1, and this is 1 by 4. 1 minus 1 by 4 means 3 by 4. 1 minus 1 by 4. This is 1 now, and this is 1 by 4. So you will get 3 by 4. Now you want to find lambda. So when you will find lambda, it will be 1 by r multiplied by 4 by 3. Now what is the value of 1 by r? 911. I told you. 911 angstrom multiplied by 4 by 3. So you can take this as okay, so this is 911 into 4. So when you will calculate this, you will get 1216 angstrom. So in this way, it will be easy when you will put the value of r in this way. Second question, n is equal to infinity to n is equal to 1. Very easy. So this you have to do. N is equal to infinity to n is equal to 1. Now this is the another, this question will be solved after this. Now spectral series. Spectral series. So these are the energy levels. This is first energy level, second, third, fourth, and so on. So if the electron is moving finally to n is equal to 1 or to the ground state from any other state, from any other state. So when the electron is moving from higher state to the lower state, it will radiate energy, and from that energy there will be a wavelength associated with it, and so you can say there will be the series of wavelength you will get. So basically when the electron is moving from n is equal to 2 to n is equal to 1, n is equal to 3 to n is equal to 1, means from any other state to n is equal to 1 if the electron is moving. So basically the series of those wavelengths will be known as the Lyman series. If for any other state electron is moving to n is equal to 2, that is known as the Balmer series. Okay, that is known as the Balmer series. And if the electron is moving from any other state, higher state, to n is equal to 3, it will be Paschen series, bracket, Fund series, Humphrey series. So in NCERT this is given, so we will stick to it only. Okay. So now if someone is saying Lyman series, so for Lyman series always remember the electron is coming to n is equal to 1, means to the ground state. If someone is saying Balmer series, so electron is coming to n is equal to 2 from other higher state. If someone is saying Paschen series, so you will take n is equal to 3. For bracket series, you will take n is equal to 4. Now we can solve this question. I think there should be one more thing. So here you can write if you want the longest wavelength emitted by the photon, longest. So there should be a shortest transition. If you want the shortest wavelength, then the transition should be longest. Longest transition. And what is the longest transition when the electron is moving from infinity to n1? This will be the longest transition. Shortest transition, longest transition. So this point you should remember for solving next question. So next question is this. Find the shortest and the longest wavelength of a Balmer series for hydrogen atom. Okay. What is the formula of wavelength? 1 upon lambda is equal to Rz square 1 upon n1 square minus 1 upon n2 square. So we do not know what is n1, what is n2. If we want to find shortest wavelength, so transition should be longest. Transition should be longest. Means electron should move from infinity to 1. Means n2 will be infinity and n1 will be 1. So put the value here. So it will be 1 by lambda r, and this is for hydrogen atom, so it will be 1 square, and it is 1, n1 is 1, and this is 1 by infinity. So what will be the answer? This will become 0, this is 1, this is 1, so it will be lambda is equal to 1 by r, and 1 by r is approximately 511 angstrom. So 511 angstrom will be the shortest wavelength. Now longest wavelength. Longest wavelength should have the shortest transition. So for Balmer series, for Balmer series, you can see it is given that Balmer series is given. So for Balmer series, n1 will be 1. Okay, n is equal to 1 na, for Balmer series. I told you take n is equal to 1 for Balmer series because electron will move from some higher energy level to n is equal to 1. So from higher energy level to n is equal to 1. That is Balmer series. Again, electron will move to n is equal to 1 from higher energy level. Okay, so oh shit, sorry. For Balmer series, n should be 2. N should be 2. N should be 2. Means electron should move from higher energy level to 2. N is equal to 2. So n1 will become here 2. It will be 2 square. 2 square means 4. Okay. So lambda. So here is 1 by lambda, no? So lambda will become 1 by lambda will become it will be 4, na? So 4 by r, and 1 by r is 511. So it will become 3644 angstrom. Now for Balmer series, the electron should move from higher energy level to n is equal to 2. So means shortest transition will be when the electron moves from 3 to 2, it will be the shortest. And this will be your n2, this will be your n1. So when you will find lambda, it will be 1 by lambda is equal to rz square 1 upon n1 square means 2 square, n2 square means 3 square, and it will be 1 by lambda Z is 1, and it will be 1 by 4 minus 1 by 9. Okay, so 1 by lambda is equal to R. So 9 4s are 36, and 9 minus 4 is 5. So lambda you will get 1 by R multiplied by 36 by 5. And R is approximately equal to 500 of 11, na? So you can take some time for the calculation purpose. R you can take approximately 510 also. Okay, because here in denominator there is 5. So lambda you can take 510 also, and this is 36 divided by 5. Now cancel this value with 5. So it will become 5 ones are 5, and this is not 511. This is 911. Okay. 1 by R is 911. So it is not R, it is 1 by R. So 1 by R is approximately equal to 511 angstrom, but for the calculation purpose, we can take 1 by R here as 510. Oh, 910. 910. So it will be 910. When you will cancel this out, you will get 182, I think. 910. 5 on the 5. 182 into 36. So you will get 6552 angstrom. So this will be the longest wavelength. This will be the shortest wavelength. Now last topic is there of this chapter, absorption spectrum. Very easy. In 5 minutes we will finish this. This is a white light, and in white light 7 color, wavelength range 400 angstrom to 800 angstrom, and you are passing this white light. Okay, you are passing this white light from some gas. Okay, from some gas. uh, so basically when you are basically white light means radiation, you are giving radiation to some gas, and this gas is at a normal temperature, you can say, or this can be cold also. So what will happen, you are providing some energy to these gas molecules. So due to the energy, uh, these gas molecule will transmit some light or transmit some radiation, and if you will pass that transmitted light or radiation from the prism, so on the screen you will get continuous spectrum with some wavelength missing. This is another phenomena. You will get the continuous spectrum, but in that spectrum some wavelength will be missing. This type of absorption spectrum you will have. Okay, this is here there is a spectrum, there is some wavelength here, there is some wavelength, but these darks are representing some wavelengths are missing. You can see in emission spectrum you are getting some wavelength on the screen and other portion is dark, but here some portion is dark, or but here it is the interesting thing is the wavelength that is missing in the absorption spectrum has appeared in the emission spectrum. So now you can see here what is the how we can explain the absorption spectrum. So when the electron moves to the higher energy level, because you are providing some white light, means you are giving some radiation to the atom. So electron will gain energy and move to the higher energy level. And when the electron move to the higher energy level, so uh, absorb electron will absorb some energy, absorb energy, na? So electron will absorb energy. So of this white light, some energy or is absorbed, or you can say some wavelength is absorbed by the electron. And you know that energy of the photon, energy means radiation or photon. Okay, so some wavelength will absorb by the electron. That is why we are not getting some wavelength on the screen. And this is the absorption spectrum. In absorption spectrum, some wavelengths are missing, but in case of the emission spectrum, some wavelengths are appearing on the screen. So you can see here the specific wavelength that appears in emission spectrum. Those same wavelengths are missing in absorption spectrum, because the difference in the energy levels will be fixed. That is why fixed wavelengths are missing and appearing. Okay, now this chapter is finished, and I have tried my best. Okay, and due to the lack of time, I have to increase my speed. Okay, so uh, after that, we have one very small chapter of one lecture, that is nuclei, and after that there is a chapter of one lecture that is semiconductor devices. So we will finish basically from now, from here, to complete your syllabus. It will take at least 2 lectures more. And if after that, if you want, then we should, if you want, then we can start revising. Otherwise, you can study by yourself. Okay. So now I think you should take the screenshots, both of you. These notes are very, very important. Now, please take the screenshots. Hmm?
Done.
Yes, sir, done.
Okay.
Done, sir.
Okay. Because from the chapter nuclei, 50% of the chapter is related from this year. 50% of the chapter. Radioactivity is basically, I will say 60% of the chapter is related. So that will not take much time. I think I can finish the chapter in 1 hour also. So, so I think there will be 2 or 3 classes more. We have.
Done, sir.
Okay. Okay.
Done, sir.
Yes, sir, done.
Okay. Okay. and please don't miss the next class because I have to complete the syllabus also. Okay, completed.
Yes, sir.
Okay, so now coming to, okay, take the screenshot. Hardly it will take 5 or 6 minutes to take all these screenshots.
Done, sir.
Yes, sir. Done.
Okay.
Done, sir.
Hmm. If you suppose if you have somehow if you have not taken the screenshot, so you can ask me to scroll up also.
Done, sir.
Okay.
Done, sir.
Yeah.
Done, sir.
Okay. So Nafisa and Nawal, when you will have the final exams started, from which date the final exams are going to start?
Do you mean boards?
Like the board exam,
Yeah, yeah.
February 16th.
Okay. So please attend the next class, okay? Please.
Yes, sir. Done.
Okay. And I think I will give you the notes also uh,
Done, sir.
after some time. Okay. Done?
Yes, sir. Done.
Okay.
Yes, sir. Done.
Okay.
Done, sir.
Okay. So this energy level diagram you will get in your NCRT also. Take the screenshot.
Yes, sir. Done.
Okay. So you can get 2 marks question from here, means what are the drawbacks of the Bohr's atomic model, and nothing more than that.
Done.
Okay.
Yes, done.
Okay. So this emission spectrum is important part. Okay. And okay, this is the continuous spectrum from the 10th class, you know. What is continuous spectrum? Okay, take the screenshot.
Done.
Okay.
Done, sir.
Okay.
Done, sir.
Okay.
Done, sir. Done, sir.
Okay.
Done, sir.
Okay.
Yeah, done.
So this diagram you will also get in your NCRT.
Yes, sir, done.
These are the questions that will appear, that may appear in your board exams.
Done. Yes, sir, done.
Okay.
Done, sir.
Okay.
Done, sir.
Okay.
Done, sir. Yes, sir, done.
Okay. So this picture is very important. This one.
Done, sir.
Okay, all of you. This chapter is finished now. According to your syllabus, I covered all the possible things, and now, depending upon you, means how much uh, you are revising and how many questions you are practicing. Now you have a limit. You have limited time, so accordingly, for me, it is very easy to say you all the do this and do this, but it depends upon you. Means depends upon your time. It depends upon your mental condition. Means what you are thinking and all that. So that I cannot explain, but accordingly, you should mm, give time to your studies. If you think that studies means this thing is useful for you, and board exams are uh, significant for you, then you should, I think, give some time to this. Okay, and so